All right, on to 3.5. Okay, so 3.5 is about local linear approximation and differentials. So let's get to it. So if f of x is differentiable at x naught, then as you zoom in to x naught, the function begins to look more and more like a straight line. We'll take a look at this in Desmos, okay, so that you understand what it is that I'm saying here. So let me, so let's take some curve. We'll call it, I don't know, y equals 2x cubed minus 3x squared, or something like that. Okay, that's good enough. So this function is differentiable everywhere, right? So so I can pick a point, like maybe this point right here, and if I zoom in on it, then the more I zoom in, the more this just begins to look like a straight line. You see that? It's practically just a straight line the more I zoom in. And you may think, well, yeah, but you chose a point that was already pretty straight to begin with. But even if you did that like right here at this point, so even if I zoomed in to that point, right, it's not looking like a straight line yet, but if I get close enough, right, if I get close enough, right, it begins to look like a straight line. It's practically a straight line at this point. Okay? And so that's true of any differentiable function. Well, it's true of any function where, you know, the function is differentiable at that particular point. To contrast that with something that's, say, not differentiable, like let's look at y equals absolute value of x. Okay. So this function is differentiable everywhere except for at 0. Remember, a function is not differentiable if it has like a sharp point, right? So it's not differentiable right at 0. So if I were to zoom into 0, you're going to see that at no point does this ever begin to look like a straight line. Okay? Like, no matter how far in you zoom, it's never going to look like a straight line, right? It's always going to maintain that sharp corner right there. So so anyway, but it is true that if a function is differentiable at a point, then, you know, if you zoom in close enough, then it's going to look more or less like a straight line, which means that at any given point along a differentiable function, you can approximate that function as long as x is as long as x is really close to the place where it's differentiable, right? You can approximate the function with a straight line. So the line that does this trick is this one right here. So f of x is approximately f of x naught plus f prime of x naught times x minus x naught. If that seems a little bit confusing to you, just think about it like this, right? When we try to find the equation for a line that goes through a particular point and that has a particular slope, then we use this formula. We say y minus y naught, or y1 or whatever, equals m times x minus x naught, right? Well, so now if you just add y naught over to the other side, then you get y equals y naught plus m times x minus x naught, and that looks awfully similar to this, right? It's just, instead of y, we're calling it f of x, right? Y naught, we're calling f of x naught. And m, of course, is just the derivative, right? The slope is the derivative. It's the slope of the tangent line. So so anyway, that's the line that does the trick. So let me give you an example. Let's say that f of x is square root of x, and let's find the local linear approximation of f at 1. Okay? Well, so 1 in this case is the x naught that we're talking about in the formula up here. So f of x naught is going to be the square root of 1. Well, maybe I'll say it like this. F of x naught would be f of 1, right? It would be f of 1, which is the square root of 1. Right? So there's there's f of x naught. Now f prime of x naught, so let's see, f prime of x, I'm thinking of this as x to the 1/2 power, so it's going to be 1/2 x to the negative 1/2, or in other words, 1 over 2 root x. So f prime of x naught, that's f prime of 1, which is 1 over 2 times the square root of 1, or 1/2. Okay, so we're ready to plug that in now and just say, okay, so f of x is approximately f of x naught, 1, plus f prime of x naught, 1/2, times x minus x naught, which is 1. And we can simplify this. This is going to be 1/2 x, and then minus 1/2. 1 minus 1/2 is 1/2. So there you go. Right? There's the local linear approximation. So in other words, what we're saying is that as long as x is really, really close to 1, square root of x is going to be approximately equal to 1/2 x plus 1/2. And that's useful because we can use that to approximate something like the square root of 1.1, right? 1.1 is pretty close to 1. And so square root of 1.1 is going to be approximately 1/2 times 1.1 plus 1/2. Let's see if we can do this in our heads, right? So 1/2 is the same as 0.5. 1 times 0.5 is 0.5, and then 0.1 times 0.5 would be 0.05. So I think 1/2 times 1.1 should be 0.55, I believe. And then plus another 1/2, so I think this is going to be 0.55 plus 0.5, so that's going to be 1.05, approximately, right? So square root of 1.1 is approximately 1.05, and I wonder, first of all, let me check my math with my calculator. Yeah, that's right. Okay, but I wonder now if we do square root of 1.1, how close is our approximation? Pretty close, right? Pretty close. To the nearest hundredth, we're right on the money. Okay, so that's not a bad approximation. So there you go. And of course, the closer that we are to 1, the better this approximation is. So if we were to do like square root of 1.01, for example, our approximation to that would be really good. It would be really close to the actual value. Okay, so here's another example, and this is maybe even more useful, right? So looking at f of x equals sine x, it says find the local linear approximation of f at 0. Okay, so 0 is x naught now, right? So so first of all, f of 0 is sine of 0, which is 0. Second of all, f prime of x is cosine x, so f prime of 0 is cosine 0, which is 1. So now plugging all that stuff in, we would say f of x, the local linear approximation of f of x is f of x naught plus f prime of x naught times x minus x naught. So in other words, that would just be x. So what we're saying is that if x is really, really close to 0, then sine x is approximately x, right? So sine x is approximately x if x is small, right? If x is close to 0. So that's an interesting fact. It's used in physics a lot, and probably therefore probably in engineering and stuff as well. So that's cool. That's good to know. So for part B, it says use the local linear approximation obtained in part A to approximate sine of 2 degrees. Okay. Well, we're not going to say sine of 2 degrees is approximately 2 degrees. We want to get a real number out of this, which means we need to change degrees to radians. And this got me into trouble in the previous section. So So let's see if I can redeem myself. So so if I want to get rid of the degrees, then I have to have 180 degrees down here and pi radians up there. 2 over 180, 180 divided by 2 is 90, right? So this is going to be pi over 90 radians. Okay, so sine of 2 degrees equals sine of pi over 90, and that's approximately just pi over 90, right? Because that's a really small number. And I wonder, pi over 90, that's about 0.035. So there you go. Let's see how good that is. So sine 2 degrees, well, that's pretty darn close, right? That's pretty darn close. So there you go. So that's it for local linear approximation. It's not a difficult concept, but it is kind of cool, I think. I'm not much of a programmer, but I wonder if that's how calculators, that might be one way that calculators do calculate trig function values. They might just do local linear approximations, but just really, really good ones, like really, really close ones or something. I don't know. There's another formula for trig functions that you'll learn about in second semester calculus. And that's probably what calculators are doing. They're probably not doing the local linear approximation thing, but who knows? Anyway, well, someone knows, right? Someone programs these things. But I don't know. Okay. So next we're going to talk about differentials, and then we'll come back to local linear approximation a little bit. So note that if dy dx equals f prime of x, then dy equals f prime of x dx, right? And just multiply both sides by dx. We haven't talked about these quantities dy and dx really yet, but these things are called differentials. And the interpretation of them is it's important to get it right, okay? So since f prime of x is the slope of the tangent line to f at x, then dy is the rise and dx is the run of the tangent line, okay? So what that means is that dy represents the change in y that occurs if we start at x and travel along the tangent line until we have moved dx units. Contrast that with the increment delta y, which you may recall from section 2.2 is the change in y that occurs if we start at x and travel along f of x until we have moved delta x units. So in other words, even if dx is the same thing as delta x, it's not necessarily the case that dy is the same thing as delta y. And it didn't leave us much room for a picture here, so I'll draw it over here in the margin. Okay, so let's say that you have, you know, some kind of curve, right? And you've got like the slope of a, or you've got a tangent line to the curve, maybe at this point right here. Okay. And let's say that you move, you know, this distance, right? So this would be, you know, this would be delta x, or sorry, dx, and then if you go from there to there, this distance would be dy. Okay. On the other hand, if you move from here to here, we would call that, we could call that dx, but we could also call it delta x. And then if you go all the way up to, you know, where that passes through the curve, that distance would be called delta y. Okay, this entire distance is delta y. Okay, so hopefully that makes some sense to you. It's like delta y, delta y is how much you're actually increasing from one point to another on the actual function itself. Dy is just the rise on the slope of the on the tangent line, right? So again, delta y is the rise on the function itself. Dy is just the rise on the tangent line. Okay. All right. So a couple of things to say, right? So let's say that y equals x squared. Then dy dx is 2x, right? Derivative with respect to x is 2x. Or equivalently, you could write that as dy equals 2x dx. And that's called the differential form. Okay? And then there's a whole bunch of other notation that kind of corresponds to that. For example, if f of x equals x squared, and we take the derivative with respect to x, we could say df dx equals 2x. Or equivalently, we could just say df equals 2x dx, right? Or if you just had x squared and you wanted to differentiate with respect to x, then you could say d dx of x squared equals 2x. Or equivalently, you could say d x squared equals 2x dx, right? So these are all called the differential forms. It's not really anything difficult, but this notation in particular is kind of nice when you're expressing, say, like, let's say that you wanted to express like the fact that the sum, the derivative of the sum of two functions is the sum of the derivative of the functions, right? You know, it's kind of nice to just be able to say d f plus g equals df plus dg. Because normally we would say d dx of f plus g equals d dx of f plus d dx of g. But you can just multiply through by dx and clear all the dx's. And so this is a more compact way to write down the same thing. But anyway, let's give you another example. So let's express the derivative with respect to x of y equals x squared in differential form. Oh, we've already done that. Let's do it for y equals sine x, let's say. So the way that we've been writing it is like this: dy dx would be cosine x, right? So in differential form, it would be dy equals cosine x dx, right? There's the differential form of the same thing. Okay? To further our understanding of the difference between delta y and dy, let's look at this example. So let's say y equals square root of x, and let's find formulas for delta y and dy. Okay, so delta y is the rise along the function itself, right? And if we relate this back to delta x, right? We can evaluate this value. We'll call this f of x, right? So this is the point x f of x, and this is the point. So maybe I'll call it x f of x. And this point right here would be, well, it would be x plus delta x, right? X plus delta x, and then f of x plus delta x. Okay, so if we wanted to figure out delta y, right, the change in y, well, it would just be f of x plus delta x minus f of x, right? That would be the change in y. So it's f of x plus delta x minus f of x. Whoops, f of x plus delta x minus f of x. So in the case where, y is the square root of x, we can call this, maybe I should have called it f, but anyway, in the case where y equals square root of x, we would call this square root of x plus delta x minus square root of x. Right, so that's the change in y. That's a formula for the change in y. Formula for dy, on the other hand, we would say dy dx is just 1 over 2 root x, right? So I'm just taking the derivative with respect to x of this function here, which means that dy is dx over 2 root x. Or you could call it 1 over 2 root x times dx, right? Whichever way. Okay? So we have those two formulas now for delta y and for dy. Now let's evaluate delta y and dy at x equals 4, assuming that dx and delta x are the same thing, that they're both equal to 3. Okay? So delta y is going to be the square root of x plus delta x minus the square root of x. That would be the square root of, when x is 4, it would be 4, and when delta x is 3, it would be plus 3. So it's square root of 4 plus 3 minus the square root of 4. So root 7 minus 2. I wonder about how much that is. About 0.65. Okay, so there's delta y. Now let's find dy, right? dy is, we said dx over 2 root x. When dx is 3, this is going to be 3 over 2 times the square root of 4. So that would be 3/4, or 0.75. Okay, so you can see that they're not the same thing. Okay, not the same thing. All right. Very good. So the main takeaway is that, you know, delta x is the increment, right? It's how much the function, the actual function itself, is increasing. The y values of the function is increasing. Delta y is it's the differential. It's how much the tangent line is increasing. Okay. All right. Okay. So back to local linear approximation. So it turns out that even though it's not generally true that dy equals delta y, it is true that as long as dx equals delta x is small, dy is approximately the same thing as delta y. Okay? In other words, dy is a local linear approximation for delta y, I guess, is the way that you can kind of say that. And that's nice. It helps us to calculate propagation and errors due to measurements when you encounter real-world measurements. You know, because when you measure something, small errors are going to occur, right? So, for example, when you measure someone's height, you may not be able to measure it perfectly, exactly, precisely. And so, oftentimes, when someone measures a height, they'll say, "Oh, I measured you at 170 centimeters, but because there's some errors, there are errors." Potentially in the measurement, I'm going to just report that as 170 plus or minus 0.5 centimeters, right? Something like that. So when researchers use these inexact measurements, which is like every time they take a measurement, right? So when researchers use these inexact measurements to calculate other quantities, they encounter error propagation in their calculations. Okay? So in other words, if I use this now to calculate, something else that's supposedly related to the height of the thing that I just measured, then I'm going to get a propagation in errors, right? Okay, so how do we express this error propagation? Well, suppose that x naught is the exact value of the quantity being measured, and f of x naught is the exact value of the quantity being computed. Or in other words, we'll call that y naught sometimes. And now let's say that x is the measured value of x naught and y is the computed value of y. Okay, then the measurement error of x is dx, which is the same thing as delta x, and that's just x minus x naught. Okay, so in other words, it's the difference between what you measured and what the exact value is. Okay, so it's the difference between what you measured and what the exact value is. Delta y is approximately dy, and dy is just f prime of x dx. Okay, that's called the propagated error of y. So So let me give you an example of this. Okay, so suppose that the side of a square is measured with a ruler to be 10 inches with a measurement error of at most plus or minus 1/32 of an inch. Estimate the error in the computed area of the square. Okay. Okay, so let's say that x, so let x be the exact length of the square. I'm calling it the length. The problem called it size. So suppose that the side of the square is 10 inches. Well, that's what it was measured to be, but let's say that x is the exact length of the square. Okay? Then the area, right? The area is the thing that we're trying to. It's the value that we're trying to compute, right? So then, and the computed value we said we would call that y. So then the area of the square is y equals x squared. Okay. So we want to estimate the error in this computed area, right? We want to estimate the error in this computed area. Well, the error is delta y, but it's approximately the same thing as dy, which is just f prime of x dx. Okay. So delta y is approximately dy, which equals f prime of x, that's 2x, dx. Okay? Now, we know that the measured value of x is 10, so we can replace x with 10 here. So we can say this is 2 times 10 dx, or in other words, 20 dx. And we also know that, so dx, which is the measurement error, is at most 32 inches, right? So in other words, what we can say is that dx is somewhere between negative 1/32 and 1/32. And if that's true, well then we can multiply through by 20. Okay, and that reduces by 4, then we'd have 5/8. This is negative 5/8 is less than or equal to 20 dx, which is less than or equal to positive 5/8. And there you go, right? So 20x is approximately delta x, so that's approximately the propagated error, right? So that's approximately the error in the computed area of the square. Okay, so yeah, so delta y, the propagated error, is equal to plus or minus 5/8 square inches. Okay, so that's that. I'll give you one more example of this, and I'm going to introduce another concept as well. So if the true value of a quantity is q, then delta q divided by q is called the percentage error, right? So delta q we're thinking of as the error. So if the true value is q and the error is delta q, then delta q divided by q is the percentage error. Okay, so for example, the diameter of a polyurethane sphere is measured with percentage error within 0.4%. Let's estimate the percentage error in the calculated volume of the sphere. Okay, so the diameter is measured within 0.4 degrees, 0.4%. We want to know the percent error of the volume of the sphere. Well, so we know that the volume of a sphere, or maybe you don't know this, but the volume of a sphere is 4/3 pi r cubed. R is the radius though, and we were given the diameter. We were given the error rate in the diameter, but that's not a huge deal. We can say let x be the diameter, then the radius is x divided by 2, right? And so in our formula, v equals 4/3 pi r cubed, we can say that's equal to 4/3 pi times x over 2 cubed. Oh goodness, now let's see. 2 cubed is 8. 8 and 4 will cancel and leave a 2, so I think we'll have 1/6. I think we'll have pi over 6 x cubed is the volume. Okay, so that's V. Alright, so V is pi over 6 x cubed. So dV is going to be pi over 6 times 3x squared dx. Or in other words, right, dV is, the 3 will cancel 3, leave a 2, right? So this is going to be pi over 2 x squared dx. Okay, we want to find the percentage error. So the percentage error is going to be this thing, which is approximately, right? So change in V, right? Delta V is approximately dV. And so delta V over V is approximately dV over V, which is pi over 2 times x squared dx divided by V itself, which we called pi over 6 x cubed, okay? If we flip and multiply, the pi's will cancel, the 6 will become a 3. So this is going to be 3 dx over x. Okay. Okay. Now, finally, we know that x is estimated with a 4%, what's the word I'm looking for? It's measured with a percentage error of 4%, okay? So we know that dx, dx over x, right, the percentage error, dx is going to be between 0.4%, negative 0.4%, and positive 0.4%. Or in other words, you could say negative 0.004 is less than or equal to dx over x, which is less than or equal to 0.004. So that means 3 times dx over x is going to be between 3 times this number. 3 times 0.004 is negative 0.012. Okay. And so there you go, right? So as a percentage, you would say, so the error in calculated volume, so therefore the error in calculated volume delta V, or the percentage error, we'll say, the percentage error in calculated volume delta V over V equals plus or minus 1.2%, right? 1.2%. Okay, 1.2%. So there you go. So that's all I have to say about that.